0. That is how many miles of maglev rail the United States operates. China has engineered a system levitating trains at 600 kilometers per hour, a 1,000-kilometer corridor budgeted at $30 billion. That alone represents a generational lead. But it is one of 10 Chinese systems now deployed at scales. American infrastructure won't reach for decades. Thorium reactors running in the Gobi. Mach 30 wind tunnels testing weapons the Pentagon cannot simulate. Quantum satellites distributing unbreakable encryption keys. This is not a technology race. It is a construction audit. And the ledger begins with speed and power. A train moving at 600 kilometers per hour does not touch the track. It floats, held aloft by high-temperature, superconducting magnets that keep it hovering 100 millimeters above the guideway. Linear, synchronous motors, powered by a 20 kilovolt, 25 kiloamp inverter, propel the 8-car set with 40 megawatts, most of which is spent pushing through air resistance rather than friction. The guideway's tolerances are kept within 5 millimeters per kilometer, with expansion joints every 500 meters to handle thermal shifts. Reliability is engineered through redundant cryogenic cooling and dual feed power, delivering a 99.7% availability rate. The Shanghai to Beijing maglev, stretching 1,000 kilometers, carries a $30 billion price tag. Civil works account for $12 billion, magnetic guideway infrastructure $5 billion, and rolling stock $4 billion. Each train set costs $150 million. The rest covers signaling, land, and startup operations. Despite the capital outlay, the economics shift over time. No wheel-rail contact means maintenance labor drops by 40%, and superconducting coils last 20 years before needing remagnetization. Annual laser-based alignment replaces traditional rail grinding and ballast work. Energy use stands at 0.1 kilowatt-hours per seat kilometer, 15% less than high-speed rail, and just a third of what short-haul aviation consumes. Regenerative braking recaptures up to 30% of kinetic energy. A maglev covers 500 kilometers in under an hour, skipping airport lines and runway delays. On the Beijing to Shanghai corridor, high-speed rail has already replaced 150,000 daily air passengers. With maglev's city center integration and a 30-minute time advantage under 500 kilometers, airlines lose their cost advantage, and the short-haul market shrinks. CRRC Changchun engineers estimate break-even at 18,000 daily passengers per corridor, with fares of 12 to 15 cents per kilometer. Capital recovery is projected within 30 years. Financing splits between government, provinces, and state banks, with internal rates of return at 8 to 10%. This is not a prototype. It is a logistics backbone, built to erase the inefficiencies of legacy transport. On October 11, 2023, a reactor core buried 14 meters beneath the Gobi Sands reached criticality. The TMSR LF-1 prototype, managed by Dr. Li Weihua at the Shanghai Institute of Applied Physics, achieved a sustained nuclear chain reaction not with uranium oxide rods, but with a circulating molten salt mixture of lithium fluoride, beryllium fluoride, and thorium. On June 17, 2024, the system completed a continuous 10-day run at 2 megawatts of thermal power, confirming both stable operation and the conversion of thorium into uranium-233. This is not a laboratory experiment. It is the world's first operational thorium molten salt reactor, running on a fuel cycle that sidesteps the uranium supply chain and eliminates the need for massive water cooling towers. The core's passive safety is engineered at the chemical level. A freeze plug of solidified salt blocks the drain line beneath the reactor. If temperature rises or power is lost, the plug melts and the entire salt inventory drains by gravity into subcritical tanks where it solidifies. No pumps, no human intervention, no risk of meltdown. The negative temperature coefficient ensures that any rise in temperature dampens the reaction rate, a self-regulating property absent from conventional pressurized water reactors. The Gobi site was chosen for its aridity and seismic stability. Unlike legacy nuclear plants, which require millions of gallons of cooling water daily, the TMSR's heat exchangers operate with air or low-flow liquid metal loops. Water usage is less than 5% of that of a comparable pressurized water reactor, and there is no high-pressure steam circuit to rupture. The entire reactor sits in a sealed dry well, isolated from the water table, and designed for rapid entombment if containment is breached. Supply chains for the salt and alloy components are domestic. Zirconium from Shanghai, specialty fluorides from Gansu. The total research and development budget, reported at 3 billion yuan, is a fraction of what a Western pressurized water reactor of the same output would cost. By 2030, a 10-megawatt demonstration plant is scheduled for full grid integration, with the aim of establishing a base load power source that is both proliferation resistant and immune to water scarcity. China is not waiting for international consensus. The physics is proven, the plant is running, and the next phase is already under construction. A single satellite, Meteus, circles 500 kilometers above the Earth every 94 minutes, carrying a Sagnock interferometer and a high-rate entangled photon source. This is not theory or simulation. In August 2016, Meteus became the world's first operational quantum communication satellite, engineered by a team led by Professor Pan Jian Wei at the University of Science and Technology of China. The payload's core function is quantum key distribution, QKD, using entangled photons to generate encryption keys that cannot be intercepted or copied without detection. The satellite's downlink connects ground stations separated by up to 1,200 kilometers. In a 2017 science paper, Pan's team reported measured entanglement distribution over this full distance, with a quantum bit error rate below 3%, well under the 11% threshold for unconditional security. Each orbital pass delivers a secure key at a rate of roughly 1 kilobit per second, enough for continuous one-time pad encryption of diplomatic or military command traffic. The limiting factor is photon loss through the atmosphere and the narrow beam divergence from a 300mm telescope. All operational logs are public. 80 kilobits of secure key were exchanged in a single pass between Xinglong and Nanshan, and 560 kilobits in a multi-session Beijing to Graz intercontinental link. The system's resilience is rooted in quantum mechanics. Any attempt to eavesdrop collapses the entangled state, producing an immediate spike in error rate and triggering a protocol abort. The United States has demonstrated ground-based QKD over 120 kilometers, but no orbital system matches China's operational coverage or error performance. The Meteus network is not a prototype. It is a deployed backbone for quantum secure communications, with direct implications for military data sovereignty and national infrastructure defense. By 2030, China plans a 6-satellite constellation, eliminating single points of failure and creating a communications shield that legacy cryptography cannot penetrate. A single production line at the National Graphene Innovation Center in Ningbo claims a continuous output of 150 square meters of monolayer graphene per hour, using roll-to-roll chemical vapor deposition. The process runs on a copper foil substrate, with methane and hydrogen as feed gases, and maintains a reported defect density under 5 billion per square centimeter, meeting the ASTM-D 7365 bar for aerospace-grade composite use. The plant's chief technology officer, Zhang Weimin, states that raw material and energy costs average 75 cents per gram, with capital and labor bringing the total to roughly $1. Production yield is posted at 99.2%, minimizing copper wastage and slashing per unit cost below any Western benchmark. No third-party metrology lab has released Raman spectroscopy or transmission electron microscopy audits confirming these numbers. The Stanford Emerging Technology Review notes that sub-dollar graphene remains a claim, not a certified industrial baseline. Conference abstracts from CS International highlight the gap between best-case pilot runs and the challenge of sustaining uniform quality over 100-meter webs. Still, the absence of independent verification has not slowed domestic deployment. Graphene-enhanced concrete panels fabricated with NGIC material have entered service in Shenzhen's Smart Barrier project, delivering a 12% increase in compressive strength and built-in electrical sensing. Aerospace original equipment manufacturers, including AVIC, cite a 30% weight reduction in unmanned aerial vehicle wing skins using graphene polymer laminates, though mechanical data remain proprietary. The battery sector is already integrating these sheets into next-generation lithium-sulfur cells, targeting a doubling of specific energy. At $1 per gram, graphene moves from laboratory curiosity to commodity input if the numbers hold. The strategic calculus is simple. Whoever controls mass-scale graphene supply controls the future of lightweight structures, energy storage, and advanced electronics. For now, China's roll-to-roll plants claim to be the only source at industrial scale. A shockwave tube 30 meters long, bolted to reinforced concrete deep in Beijing's western suburbs, is the heart of the JF-22 wind tunnel. Here, hydrogen and air mix under pressure, then ignite in a controlled detonation, driving a blast of plasma-heated gas down the test section at speeds up to Mach 30, 10 kilometers per second. The facility's driver mechanism, a staged combustion system, delivers sustained hypersonic flow unmatched by any Western test site. The core chamber is lined with ablative ceramics and instrumented with high-speed pressure and temperature sensors, capturing boundary layer transition and shock interactions in real time. Construction cost exceeded $100 million, funded by the China Aviation Industry Corporation and the Institute of Aerodynamics. The tunnel's annual runtime, over 5,000 hours, triples the combined capacity of the largest American hypersonic tunnels. This allows engineers to compress the design-test-redesign cycle for hypersonic glide vehicles from years to months. The JF-22 test director, a former PLA Air Force researcher, oversees a schedule that prioritizes strategic weapons validation, with test articles ranging from maneuverable warhead bodies to ceramic heat shields. No independent pressure time histories or peer-reviewed performance logs have been released, but the tunnel's operational throughput and its role in China's rapid hypersonic deployment is not in dispute among aerospace analysts. The United States, constrained by legacy infrastructure and cost, cannot match this pace. In the race for hypersonic supremacy, the JF-22 is a force multiplier, an industrial asset engineered to erase the margin of error from flight physics and turn computer simulations into deployable weapons. 8 towers rise along the Liujiang River, each clad with modular panels supporting a living facade. 30% of the exterior surface is covered by automated irrigation plant owners and vertical biofiltration units, maintained by a city-funded horticultural staff. Completion was logged in early 2024 under the Luzhou municipal government, with the Green Architecture Institute supplying the sensor array. The system's core metric is passive cooling. Embedded temperature and humidity sensors record an average summer reduction of 3 degrees Celsius compared to adjacent conventional towers, verified across 2 consecutive July to August cycles. Data collected from over 400 sensor nodes show that direct solar gain is cut by 22%, and heating, ventilation, and air conditioning energy demand drops by nearly a third during peak load hours. The greenery's evapotranspiration effect, modeled using Luzhou's urban microclimate baseline, accounts for most of the measured difference. However, the absence of independent environmental audits and the lack of open particulate or carbon dioxide absorption logs leave the full impact unverified. Maintenance costs and long-term plant survival rates remain undisclosed. The project stands as a municipal-scale demonstration of bio-urban engineering, but its claimed efficiency gains have yet to be substantiated by third-party review. In 2025, China launched its first 0.3 terahertz experimental payloads aboard a Long March 11, marking a new phase in satellite communications. Overseen by the Ministry of Industry and Information Technology, the mission's DFH-5 bus carried photonic integrated circuits and cryogenic receivers engineered to suppress thermal noise below 2 Kelvin. Achieving reliable detection at these frequencies demands submicron alignment and advanced vibration isolation, pushing the limits of current materials science. Atmospheric attenuation models, once theoretical, are now being tested at altitudes above 30 kilometers. Early link tests report a bit error rate of 10 to the minus 9 across a 1,500 kilometer ground to orbit path, with throughput surpassing 1 terabit per second. Phased array antennas with 0.2 degree agility enable massive MIMO and electronic handover, while spectrum rights secured through ITU filings in 2024 block rival orbital services. The program's rationale centers on real-time remote control of automated mining operations and offshore platforms, where sub-millisecond latency is essential. With a budget of 12 billion yuan, 3 more prototype launches and ground stations in Xi'an and Chengdu are planned. Success in cryogenic receiver reliability will shape global 6G standards, embedding China's protocols at the foundation. 110 meters above the Bohai Sea, the Blue Whale 2 platform anchors a new frontier in energy extraction. Commissioned in 2024 by China National Offshore Oil Corporation, this semi-submersible structure is engineered for the industrial harvest of methane hydrates, crystalline compounds of water, and natural gas trapped beneath the sea floor. The platform's dual-layer drilling rig penetrates to depths exceeding 2 kilometers, where pressure and temperature keep gas hydrates stable within marine sediments. Extraction relies on depressurization. By lowering ambient pressure in the borehole, hydrates dissociate into methane and water, which are then separated and routed to onboard liquefaction trains. The process is monitored by a closed-loop cryogenic system, maintaining thermal gradients that prevent premature gas escape and hydrate reformation within the well. Blue Whale 2 targets an annual output of 10 million metric tons, a scale unmatched by any Western pilot. The physics are unforgiving. Hydrate decomposition must be precisely balanced to avoid catastrophic slumping or uncontrolled gas release. No independent reservoir modeling or environmental audits are public, but China National Offshore Oil Corporation documents cite a 97% methane recovery rate and a levelized cost below the cost of conventional offshore liquefied natural gas. The platform's strategic value is clear: direct energy capture from oceanic reserves, bypassing pipeline choke points and foreign supply chains. In a region where energy independence is a matter of national security, Blue Whale 2 stands as an autonomous node, industrial, continuous, and engineered for the deep sea. In 2022, a 5-story apartment block in Shanghai rose from its foundation not through traditional scaffolding, but by the layered extrusion of concrete from a 12-meter wide print gantry. The Winsun 3-dimensional printer, managed by project engineer Zhao Ming, deposited a geopolymer mix at a rate of 60 cubic meters per hour, guided by a digital model that mapped every wall, void, and utility chase. The site consumed 320 metric tons of recycled aggregate and fly ash, with total construction waste measured at just 4%, down from the industry average of 15%. Labor requirements were slashed by 80%. A team of 8 supervised the print run, compared to the 60 workers needed for a conventional build. The process eliminated formwork, reduced rework, and enabled continuous operation through night shifts, pushing throughput to levels unattainable by manual trades. Yet, despite the speed and material savings, the structure's occupancy certificate remains provisional. No independent agency has published compressive strength or seismic durability data meeting ASTM or Eurocode standards. Winson's print cluster demonstrates a radical cost curve, but until third-party certification is secured, its role in permanent urban housing remains a calculated risk. The automation, however, is irreversible. Every job site that deploys this system shifts the labor equation, raising questions about workforce displacement and the future of skilled trades in construction. 10 million sensors embedded across Hangzhou feed a single data pipeline, processed in real time by Alibaba's City Brain. The platform's neural network parses traffic camera feeds, GPS pings, and utility meters, generating a live urban map with millisecond latency. Every intersection, bus, and emergency vehicle is tracked. Their positions and velocities recalculated at up to 1,200 times per second. The system's dashboard displays congestion metrics, vehicle flows, and incident alerts, with control algorithms adjusting over 1,300 traffic signals on the fly. Since deployment in 2020, Hangzhou's published traffic data shows a 15% drop in average congestion citywide, measured by travel time per kilometer across peak hours. Ambulance response times have improved by 7 minutes, attributed to City Brain's dynamic routing and preemptive signal clearing. The platform's architecture scales horizontally. Each new sensor, from air quality probes to parking meters, is integrated into the same graph-structured data model, allowing cross-domain optimization. Alibaba Cloud's annual operating cost for City Brain is reported at 300 million yuan, while municipal productivity gains, calculated from fuel savings, reduced idle time, and faster logistics, are estimated at over 1 billion yuan per year. The head of City Brain Engineering, Wang Jian, describes the system as a synthetic nervous system for the city, where every node and actuator is coordinated by AI inference rather than human command. No new roads have been built, but the throughput of the existing infrastructure has been raised to a level unmatched by any Western benchmark. The result is an integrated urban grid, managed as a single, adaptive machine. China's approach is not speculative. It is deployment at industrial scale, measured in gigawatts, kilometers, and terabits per second. Each system operationalizes decades of investment and state strategy, shifting the axis of global advantage from theory to implementation. The contest now unfolds in real time, with infrastructure as the currency of power. The pace of engineering, not ideology, sets the new threshold for leadership.